Okay, so this is the last lesson of Unit 1, and unfortunately, arguably the toughest. So, what we're going to do is review the ideas of what an intermolecular force is, and then we are going to review how to do Lewis structures. So this will be like an extra thing at the end of a question. So the intermolecular forces are listed here in order of strength: hydrogen bonding, dipole, dipole, and London dispersion forces are the weakest. So when we talked about intramolecular forces, ionic, covalent, metallic, deciding whether which ones of those are stronger is not really something we needed to do. Though all of those forces are stronger than intermolecular. However, intermolecular forces, the strength differences in the three types is very, very important. So we use dotted or dashed lines to show that these forces are weaker than intramolecular, and then the type of the force can then be used to decide if it is stronger or weaker. And they are between molecules, which means they are for covalent compounds only. As they are weaker, they are formed or broken during physical changes. The stronger the intermolecular force, the more energy needed to break the molecules apart. So if you're given boiling point data, the higher the boiling point, that means more energy is needed to get them apart, and that means that the force is stronger. So when we draw these diagrams, you have already figured out how to draw a polar covalent molecule like hydrogen fluoride. And then if you had more than one molecule of hydrogen fluoride and you were going to show the forces between them, all you would do is this dashed line or a dotted line to show the attraction. So we will talk about when or how the molecules are attracted, so slightly negative, slightly positive. Opposites attract in chemistry. And you can use the bubbles to show intramolecular like we have before. This is just a way to represent that the forces, intermolecular forces, are not as strong. Okay, so the weakest force is London dispersion forces, named after a scientist, London. You can call them London forces, you can call them dispersion forces. If you speak to a grade 12 student, they probably will call them LDF forces. So when you have a London dispersion force, these are the weakest because they are a temporary imbalance. They are produced in a moment, instantaneous, that you have an attraction between two molecules or trillions of molecules if you have a giant vessel of them. And these molecules you wouldn't think have forces between them, like nonpolar. So when we draw nonpolar molecules, we do not draw the slightly positive and slightly negative like we did in the HF example. So you would say nonpolar means equal sharing of electrons. Why? How is it possible that they could be attracted to each other? So what happens is that the a molecule is it's possible to induce a dipole in another molecule. So if you have a magnet and you put it near a molecule, or the electrons are always, always, always moving and spinning, that maybe in an instant, one side of the molecule, the electrons have spun toward that side and made a slightly negative spot, which would then induce in a neighboring close molecule, it would induce a slightly positive attraction, or it would change its dispersion of electrons. They and then so on and so forth. So because when you have a sample of molecules, there would be trillions of molecules. The attraction between them continuously forms and breaks, even though it only lasts for such a brief amount of time. And so, well, on the next slide, we'll talk about how dispersion forces can be stronger or weaker depending on the size of the molecule. So, yes, they are found in all molecules, nonpolar and polar. However, they are the only important force in nonpolar molecules. So, when you give a reason for what type of force is present, then you can say that nonpolar molecules have London dispersion forces. Other types of molecules, like polar covalent, have stronger forces, so they are the important force. London dispersion forces are not going to influence the properties of those molecules like they do nonpolar. So the forces between these molecules are weak because the dipole exists technically only for a moment. Yes, they are forming and breaking and forming and breaking and forming and breaking. However, they are not permanent dipoles. There is no slightly positive permanent and slightly negative permanent. They have to be very close together, and the larger the molecule, the more so the more electrons and protons are able to attract to each other, making the dispersion forces stronger. And this is really what we're going to use in chemistry and biology as well, to help us describe these forces. Okay, so we have, let's say in our example, we have methane. Methane has one carbon. We have There are hydrogens as well, but you can even just count the number of atoms. So which the more atoms you have, the more electrons there will be, but you can even use this simple example. So methane is natural gas. It's the gas that comes out of our Bunsen burner taps. It is a very nonpolar molecule. If you did the um, electronegativity difference between carbon and hydrogen, you would get in the nonpolar range. And so what that means is then if it's nonpolar, you would say, okay, the only important force is London dispersion molecules. And you could draw a CH4 molecule and another one. Carbon or hydrogens are usually considered filler. Yes, you could draw London dispersion forces between them, but we'll keep our picture less cluttered. So one carbon technically means one spot for dispersion forces to form. That is not very strong. So even within London dispersion forces, there is a difference in the strength as well. Do we have to worry exactly where this spot for London dispersion forces to form is? No, we are using this red dotted line as a model. They don't really look like this. Okay, and then if we look at octane, which is in gasoline. So when you pump gas in your car at the gas station, it comes out as a liquid. So why is that gasoline a liquid? So octane, oct means eight. So there are eight carbons in a row. So if we had two molecules of octane and we drew them like we drew the two molecules of methane, then you could draw the dashed lines between all eight of the carbons in each of the chains. So technically, you would have then eight spots where dispersion forces could form. So you can see as you're drawing all these spots, you can think of them like hands that are holding. You could think of them like chains between the two molecules, whatever. If you have 8 spots for something to form, then that is going to be stronger than one spot. So these for London dispersion forces in a molecule like octane, which is clearly bigger, it's a very large molecule compared to methane, they are going to have stronger forces. And so the strength of the forces in terms of their physical properties is vital. So if you have 8 spots, excuse me, for dispersion forces to form, that those are going to be stronger forces, which means that it's a liquid at room temperature. When you go to pump gasoline in your car, it is a not a gas. It is a liquid, which means that you can't just use a flint lighter to ignite it. Imagine if that's all you had to do was a little bit of friction to get the gasoline in your car to ignite. Your car would be exploding all the time. Whereas the weaker forces in methane are going to mean that it is a gas at room temperature. So for us in our classroom, it is easy for us to ignite that lighter. If you have a gas dryer at home or a gas stove, all you would need is a spark from your pilot light. Usually your parents would call it the pilot light, and it can ignite. So as human beings, we make use of these London dispersion forces. Okay, so the next force is dipole-dipole force of attraction. And this one makes a little bit more logical sense. So scientists sort of discovered this discovered or described London dispersion forces sort of um, after dipole-dipole and hydrogen bonding. So when you have a dipole force of attraction, this is between polar molecules. So polar molecules have a slightly positive end and a slightly negative end, right? So when you do step number one, you would draw or you would calculate the change in electronegativity. So I chose here hydrogen and chlorine. So hydrogen's electronegativity is 2.2, chlorine's is 3.16 equals 0.96 polar covalent. Normally, we would not draw the Lewis structure as is drawn here. This is called a space filling model. The reason I chose this picture for this note, because we've already drawn polar covalent Lewis structures, you know how to do that, is because of the way this is drawn. So the hydrogen looks smaller because its negative charge is less. Chlorine has a larger negative charge, and that's the way this picture has been drawn. Okay, so on this picture, the hydrogen and chlorine is labeled. The intramolecular force, the polar covalent bond, is labeled with a straight line because it's stronger. And then the dotted line in between the slightly negative end, which is the chlorine, and the slightly positive end, which is the hydrogen, is the intermolecular traction or dipole-dipole. So when you have this kind of attraction, it follows the opposites attract rule of chemistry. So the attraction occurs between the slightly positive end of one of the molecules and the slightly negative end of the other. So when you do questions, you're going to do the change in electronegativity first. You have to know whether it's polar or nonpolar. Because if it's nonpolar, the most important force is London dispersion. And then if it's polar, there's a little bit of choice. So when we're representing intermolecular attractions, even though this is dipole-dipole, it still looks similar to what we did with London dispersion. All we're using is a dashed line or this perfect dotted line because we're trying to show the intermolecular force between molecules is weaker than the intramolecular force, which is between the hydrogen and the chlorine atoms. So in the end, it's more about the type of molecule than trying to draw the picture a different way. That's not what we do. Including the slightly negative and slightly positive in the Lewis structure is very important. We need to know where the slightly positive end of one molecule is and where the slightly negative end of another is. That's where the attraction occurs. Okay, and then the strongest intermolecular force is hydrogen bonding. And those of you that are taking biology as well, you will talk about hydrogen bonding because it is a very important force for life on Earth. The hydrogen bonding exists between our DNA strands to make them into the double helix, and of course in water as well. So when you have a hydrogen bond, it is the molecules that contain the important atoms for hydrogen bonding are also polar covalent. So once you do the change in electronegativity and you discover that a molecule is polar covalent, then there's an extra step and you have to decide, is it going to be dipole-dipole force between the molecules or is it going to be hydrogen bonding? So for hydrogen bonding, you want to look for hydrogen, has to have hydrogen, and then fluorine, oxygen, or nitrogen. And sometimes students will shorten that or chemists to FON or NOF. So when hydrogen is bonded to extremely electronegative elements, the NO and F is going to be quite large, the change in electronegativity between nitrogen and hydrogen, or sorry, yeah, oxygen and hydrogen or fluorine and hydrogen, and it's almost ionic. So these are so polar that their forces between them are very strong. So when you look at the graphing worksheet after the note, then you can make the graph and clearly see. Methane, which we already talked about, was nonpolar. Its boiling point is a negative 159 degrees Celsius. Water's is 100, and they're essentially the same size molecule. So then the idea that a larger molecule should have stronger forces doesn't work. So why do these molecules, HO, HN, and HF, have such strong high melting and boiling points, these physical properties? Why? It's because of their hydrogen bonds. So these, like I said, HF, HO, HN are very polar covalent bonds. So then one end of the molecule is slightly negative, the other end is slightly positive, and the charge difference between them is quite high. And it has to also do with the size of the hydrogen atom. It's so tiny, it has a low electronegativity, and so the formation of the hydrogen bonds is important. So when you, again, so we're still using the dotted lines or the dashed lines to represent the intermolecular attraction. It's not anything different with the water molecule. So this happens to be water, H2O. Then when you drew the Lewis structure, you would go in and label every oxygen as slightly negative, every hydrogen as slightly positive. There should be two pairs of electrons on oxygen. I left those out of this diagram because it's cluttered enough already, but they would be in there too. So when you have this type of picture, the indication of where the hydrogen bonds form comes from the difference in electronegativity. So oxygen has a higher electronegativity. Every single oxygen has to be labeled slightly negative. Hydrogen has a much lower electronegativity. That means it's way less greedy for electrons. So every hydrogen should be labeled slightly positive. Okay, so again, we're just using dotted lines or dashed lines to show where those hydrogen bonds are forming. There is nothing, here I've used a red color. I think I used red on another slide as well. That's up to you. That doesn't matter. It's more about the dashed lines. The solid straight lines are reserved for the type of intramolecular attraction, which will be um, polar or nonpolar covalent. Remember, no metallic and no ionic, they do not have intermolecular forces between their molecules. It's not a thing. And water's extra unique because this shape here of the water molecule, the 3D shape is called angular, which we'll talk about in grade 12. But when you have this sort of attraction between the molecules, you can see there's space in between the water molecules, and that space is bigger when the molecule is a solid, which means that ice floats. So water floats when it's a solid, it does not sink. Imagine if every single winter the solid ice, the solid water sunk and crushed everything inside a lake or a river. It floats, it doesn't do that, although it's causing problems right now when it's melting and flooding and ice jams. But um, even intermolecular forces, even though they're weaker, doesn't make them any less important. Okay. So, if you get a question and you're asked to predict the type of intermolecular force between molecules, how are we going to do that? So, again, we're going to do the change in electronegativity first. Ionic compounds, if it was ionic, you would use square brackets and plus minus to show, or in the Lewis structure, and then nonpolar or polar covalent, you would have either the bubbles or the lines and slightly positive or slightly negative. So ionic compounds is transferring of electrons. There's no intermolecular force. And I'm not going to ask tricky questions like, oh, here's sodium chloride. What kind of intermolecular force would it be? And you would have to say, no, it's ionic. We're not going to do that. So there won't be questions about intermolecular forces and ionic compounds related to each other. When you do the change in electronegativity and you get polar or nonpolar, then we're going to focus on the strongest applicable intermolecular force. So yes, all nonpolar and polar molecules have London dispersion forces, as well as if it's polar, you could have dipole-dipole or hydrogen bonding. We are not going to worry about those, as talking about London for polar as well. So nonpolar is equal sharing of electrons, which means when you do the Lewis structure, you would not draw slightly positive and slightly negative. London dispersion is the only important force in nonpolar. For polar covalent, that's unequal sharing. And when you have a change in electronegativity value in the polar range, then and you were asked to draw the Lewis structure, you had to put in the slightly positives and slightly negatives. For when you're asked to determine or predict the type of intermolecular force, we also have to look at the type of atoms. So usually I tell students to do part A will say determine the type of bond using change in electronegativity. Then you will draw the Lewis structure, and then you'll be asked to predict the force. Not draw the force, just predict the type. So when you have polar, I recommend that you check for hydrogen bonding first. So hydrogen bonding requires a hydrogen on one molecule and nitrogen, oxygen, or fluorine on another molecule. So check for those elements first. So we did HCl. It had hydrogen. No, it had chlorine though, not NO or F. So no hydrogen bonding. So check for those atoms first. And if it doesn't have that, then it's going to be the other type of force, intermolecular force, that exists between something with a permanent dipole, which is dipole-dipole. And when you write your reasoning, you can even say the force is going to be dipole-dipole, molecule is polar, but no hydrogen bonding possible. So check for hydrogen bonding first. Okay, so this would be a typical type of question. Use change in electronegativity to determine the intramolecular bond. Again, ionic, yes, you can do that, and then that helps you decide what kind of Lewis structure to draw. But for ionic, there would be no part C. Okay, so we're going to do three examples. We're going to do a nonpolar and a polar dipole, polar hydrogen bonding, no ionic. Okay, so chlorine gas is two chlorine molecules. It is one of the diatomic molecules. So when you do the change in electronegativity, you can show the work here. You could just put zero, but that's okay. So zero, change in electronegativity of zero is non-polar covalent, which means no slightly positive and slightly negative on the Lewis structure. You can do bubbles or lines in the Lewis structure. It does not matter, but remember to not do both. We are trying to represent sharing, so there are not ions. These molecules do not conduct electricity. I'm going to draw this Lewis structure. I'm going to draw the extra electron that needs to be shared in the middle just to make my bubbles look nicer. You don't have to do that. Chlorine is in the seventh column. If you on the periodic table, if you skip the transition metals, it has 7 valence electrons. So I'm going to draw the one that bonds together in the middle, but it doesn't matter. So then I can draw my bubble. There is the pair of electrons being shared, or you can draw the lines. You do not need to draw both if you prefer one version over the other. And remember, I'm not going to ask you to draw the intermolecular force. So you don't have to stress about whether you use lines or bubbles. In biology, in grade 12 chemistry, we will, but for now, it's all good. Okay, so once it's nonpolar covalent, London, the only intermolecular force that matters or is applicable is London dispersion force. And again, you can say London force, you can say dispersion force, you can say LDC or LDF, sorry. Same thing with nonpolar covalent. If you write NPC, that's fine. But you can't just say covalent. You have to distinguish between polar and nonpolar. And that's why the change in electronegativity is important. You do not need to memorize the periodic table. You do not need to memorize the electronegativity values. You just have to know how to use that chart at the back of the periodic table. Okay. And then the next molecule is ammonia, NH3. So we're going to do the change in electronegativity. Nitrogen is 3.04. Hydrogen is 2.2, which gives us 0.84, which is polar covalent. So when we draw the Lewis structure, yes, we have to include the slightly positive and the slightly negative. But the general shape of the Lewis structure is similar. We can do the bubbles, we can do the lines, but nitrogen is a sneaky, sneaky column. So it is a column of If you skip the transition metals, column number 5, which means there is going to be 3 bonding spots and 1 pair of electrons left over. And really, if you, let's say you forget how to draw the Lewis structure, you could do the part C with this information only. You don't actually need the Lewis structure to do the intermolecular force. So try to get marks where you can. Okay. So with this case, you can probably do never eat shredded wheat. Start at the top with your Lewis dot diagram. Remember there are 5, nitrogen has 5 valence electrons. So one at the top, one at the side, one at the bottom, and then you go back and pair the one up at the top. And again, hydrogen is in the first column, only needs 1. If you draw it next to the nitrogens, then you can show where it's going to be shared. You can do bubbles, you can do lines, you don't have to do both. And in either situation, you want to make sure to include the slightly positive and slightly negative. So nitrogen has a higher electronegativity. 3.04 is higher than 2.2. So the nitrogen is going to be slightly negative. It is more greedy for electrons. And the hydrogen is going to be slightly positive. So make sure you label all of the hydrogens slightly positive. And again, when you're done your Lewis structure, you want to make sure that I know that you know it is not going to be the nitrogen that's slightly positive. You want to make sure I can tell you mean the hydrogen is slightly positive. And do your best. I'm not great at drawing the sigmas. If it looks more like a complete 8, that's okay. It's tough to do. Okay. So again, yes, part C is doing the intermolecular force, but you could certainly have done that after figuring out its polar covalent. So you can do now it's polar covalent. We need to check. Is it possible for nitrogen and hydrogen to hydrogen bond with each other? And the answer is yes. It has hydrogen on as part of its molecule, and there is going to be a nitrogen. So if we were going to draw the hydrogen bonding, it would be a dotted line between the hydrogen and a nitrogen. So nitrogen is part of FON or NOF, the 3 electronegative elements required for hydrogen bonding to form. Okay, and then last but not least, carbon dioxide. This one's sneaky, so watch how I draw the Lewis structure carefully, and maybe you want to use bubbles for this one. Okay, carbon is 2.55. Its electronegativity, oxygen's is 3.44. When you do the subtraction, it's 0.89. That is polar covalent. So yes, we're going to draw in slightly positives and slightly negatives. And so when you draw this molecule, it's going to have double bonds, okay? So that is a little bit tricky. So carbon is in the 4th column. it's going to have four valence electrons. You might as well just draw them as never eat shredded wheat. And then oxygens, I'm going to draw the two extra pairs of electrons on the outside. It has six. It needs to make two bonds. And then I'm going to draw the bonding pairs on the inside. So oxygen needs to have two bonds, carbon needs four. So when you have two oxygen atoms, as shown in the formula, or carbon dioxide, there can be sharing with between two electrons on each of the atoms. And then we need another oxygen and two more bubbles. And now each of them has eight, a complete eight, and covalent bonding is possible to have double bonds. We are going to draw the slightly negative for each of the oxygens. It has an electronegativity of 3.44, and the carbon is less electronegative, so it's going to be slightly positive. I would not give this on the test, this type of Lewis structure. However, even if I did, then again, you could do part C without doing the Lewis structure. Yes, this one is definitely tricky. So yes, it's polar covalent. First things first, we should check for hydrogen bonding. It does have oxygen. It does not have hydrogen, which means no hydrogen bonding. So the other option for polar covalent will be dipole-dipole. Don't forget to draw in the slightly positives and slightly negatives when it asks for a Lewis structure for polar covalent molecules.